I am Valeriian Mufteev, the author of C3D Fayekov modular section of the geometry kernel C3D. My report is devoted to the features and advantages of Fayekov modeler. Curved lines and surfaces that form the geometry of technical products often directly determine the functional characteristic of the designed products. It is logical to call such curves and surfaces functional. Often, the aesthetics of a product is one of the important consumer properties of the product. Therefore, aesthetic curves can also be classified as functional. Based on the analysis of point-particle motion along a curved path, requirements for quality of the functional curves are proposed. A high order of smoothness, a minimum number of curvature extrema, minimization of the maximum value of curvature and its variation rate, minimization of the potential energy of the curve. Aesthetic curves must also satisfy the listed requirements of fairness and only then be analyzed for compliance with the laws of technical aesthetics. Smoothness is a property of function of a curve or a surface, indicating that the function can be differentiated. Different types of design use splines of different orders of smoothness. For example, when designing round routes, clathoid splines are used and smoothness of at least the second order is ensured. For profiling the camshaft cam of high-speed engines, smoothness of at least the third order is required. To ensure continuity of the torsion function when modeling space curves, the curve must have third-order smoothness. A space curve with smooth torsion should have fourth-order smoothness, which follow from the analysis of spatial curvilinear trajectory of the point particle. Only spline curves of the fifth degree or higher, at least fourth order of smoothness, provide a smooth change in torsion and can be used to model functional curves. With functional geometry, a low value of potential energy is decisive for the operational characteristic of the product. Less potential energy means less energy consumption during operation. In essence, Fayekov modeler is a geometry curve for designing products with functional geometry. It was originally intended to support the development of applications for CAD systems. After adaptation, it is included as part of the C3D geometry core of C3D Labs. Methods for modeling class F curves include the following. 1. Structuring a curve on a geometric determinant, determining inflection points and dividing the curve into separate locally convex regions. 2. Creating virtual curves. 3. Isogeometric approximation of virtual curves. The mathematics of C3D Fayekov modeler is based on parametrization. With its help, we generalized the concept of spline as a set of curves that have equal geometric parameters at arbitrary points of the base polyline. In conventional splines, the parameters of the curve are equal only at the junction of spline segments. The first innovation is that the basis of defining a spline is a set of double osculating conical curves on a locally convex base polyline. Adjacent curves form a lens on a common polyline segment. The spline tension is characterized as the deviation of adjacent analytical curves of the base spline. It can be easily estimated visually by the size of the lens between two adjacent curves. The second innovation is an algorithm for generates points of a virtual curve, V-curve, based on a spline constructed using a discrete set of double osculating conical curves. The V-curve method has the following important features. It gives the least number of extreme values of curvature. It has the duality property, since a V curve can be defined by both base vertices and tangents, like conical curves. It has a fine invariance. It exhibits low sensitivity to the distribution of vertices along the curve. The sequence of this operation in the limit defines a virtual curve of class C5. These features allow conical curves to be modeled geometrically exactly. The third innovation is an isogeometric approximation of a virtual curve with a non-uniform rational Bezier spline. It is a method for isogeometric Nurse curve creation. A geometrical algorithm consists of a series of simple operations as follows. First, double osculating conic curves on a shared segment of the base polyline are considered as second-degree Bezier curves with two segment B polygons. Second, Bezier curves are transformed to the third degree with three segment B polygons. Third, the resulting B polygon is created by averaging the initial B polygons. The middle segment of the resulting B polygon is parallel to the initial segments and is at an equal distance to them. Since the averaged B polygon is also convex strict, as the geometry is preserved. The fourth innovation is the isogeometric approximation of a virtual curve with a B-spline curve. The key concept here is the rejection of conventional approaches when the vertices of base polyline should coincide with spline nodes. A spline should pass through the vertices of the base polyline, but spline nodes, or any spline points with fixed parameters, do not coincide with the base polyline vertices. The algorithm is heuristic and is similar to manual editing of S-polygon. Initial tangents at V-curve points are used, and tangent intersection are the S-polygon vertices. In the current iteration, the point-to-spline distance are estimated on the S-polygon. To minimize errors, a tangent is shifted parallel to itself by the error value. Then the iteration is repeated, making the proposed isogeometric approximation algorithm a heuristic geometrical procedure. The next question arises: why class F curves but not class A curves? In the given pictures, a generated B-spline curve from the given set of points on a circle by using Siemens NX software and C3D Fay curve model illustrates the difference between class A and class F curves. As it can be seen from the example, class A curves do not provide a desired performance. There is another magic option. This is the option of fixing the tangent on the global spline. How does it work? It is implemented as follows. We enter auxiliary non-native points on the polyline. Fix the required direction in the native points. The algorithm changes the position of the non-native points to ensure the required direction of the tangents and builds a high-quality global spline that passes exactly through the native points with fixation of the tangents. The method of constructing a curve on a tangent polyline was liked by aircraft designers. From the official presentation of Compass 3D version 22, constructing a wing profile on a tangent polyline. The differential characteristics of the spline curve are determined by the divided differences of S-polygon in float format. Therefore, a harmonized, correct, regular shape of the S-polygon in float format is a necessary condition for the high quality of the spline curve. A technique for modeling a curve on a S-polygon in an open format has been developed. The approximation of virtual curve reduces to the construction of a second-order Hermite GD and then the construction of a Nurse curve or a B-spline curve. We can use the same scheme of approximation analytic curves. In math system, we form Hermite GD on analytic curves. In web fake curve modeler, we construct a NURBS curve or a B-spline curve. Then transfer the NURBS model to the CAD system. If curve in spline Bezier format, curve on spatial polyline taken from the helix primitive. Two remarkable analytical curves are introduced directly as construction commands into the fake curve modeler system. Clathoid, a curve with monotone linear curvature. Maclaurin sectrix, a curve with monotone curvature defined in an osculating triangle. A technique for constructing transition rational B-spline curves of high degrees have been developed. The original curves can have an arbitrary format and degree. In this example, a rational B-spline curve of 6 degrees connects two segments of a circle. The integral curve has fifth order of smoothness. Many experts consider the physical spline to be ideal for engineering curves, for example, for ship contours. It is believed that the physical spline curve minimizes the potential energy of the curve. We executed a comparative test. We took a flexible ruler and deformed it with weights. It turned out that F curve, constructed on the same initial polyline as the physical spline, has a smaller variation and curvature, a lower value of potential energy. Of course, a curved bar simply clamped at both ends does have minimal potential energy. No one argues with this, but for a physical spline deformed with weights, this turns out to be not the case. The F curve has less energy. This is a phenomenal and inspiring result. The frame kinematic scheme of construction allows to bring the procedure of surface construction to two stages: construction of the frame of forming F-NURBS curves on a uniform grid, and construction of the frame of the directing of F-NURBS curves on the frame of control spline of S-polygon. S-polygons of directing F-NURBS curves are united to S-frame of B-spline surface. Advantages of methods of isogeometrical modeling of F-curves are generalized to methods of construction on surfaces. In this example, the vertices of the polylines belong to a torus. The right figure shows an image of two superimposed surfaces, a torus and B-spline surface. In this technique, adjacent compartments share subareas of floating S-frames to ensure overall smoothness. In addition, a technique for matching B surfaces by constructing them on a base point network was developed. When modeling topologically complex surfaces as mosaic of B-surf, areas that are not homeomorphic to the rectangle inevitably arise. Such areas arise at the fuselage wing junction and on the wing tip. Such areas arise at the junction of the vessel's bulb with bow. Based on Forest method and function of fair curve modeler, we develop a procedure for constructing a topologically complex patch in the form of a recursive scheme of successive embedding of compartment of B-spline surfaces into a topologically complex patch. The float format of S-frame allows the implementation of the Forest method in fair curve modeler. For example, when modeling a one-sided surface of the Klein bottle type. This example is the simplest, but it shows the efficiency of the method. The entire integral surface has the fifth order of smoothness, including the seam. These properties of F-curves make fair curve model the ideal geometric kernel for modeling functional geometry in engineering. The application of class F-curves and surfaces are shown below. These include tillage implements, aerodynamic profiles, external surfaces of aircraft, ships, cars, profiles of compressor and turbine blades, propellers. To test the concept of good geometry, good product, the shape of the standard plow was improved. The plow design was thoroughly tested in the CFD system Flow Vision from TESIS, and then tested on a soil channel and in field trials, which showed a paradoxical positive result. The quality of plowing was improved and fuel was saved at the same time. Critical wing profile after measurement on a scanning device and direct construction on the measured points and after smoothing in a given corridor. This example impressed the expert of C3D Lab so much that an image of smoothed profile is used in the advertisement of C3D Feuerkurve modeler on the company's website. Abbott's method for modeling airfoils NASA 4-digit uses a reference profile as Bezier curve of 8th degree, which is then superimposed on the profile's midline. The midline in the method is modeled as a 2nd degree Bezier spline curve of 1st order of smoothness. Here we note that the order of smoothness of the resulting curve coincides with the smallest order of smoothness of function included in the superposition. In this case, the smoothness of the wing profile will be of the 1st order of smoothness. This is a significant drawback of the method. An obvious direction for improving the method is to construct a reference profile in the form of B-spline curve based on measured data with the smoothing option and construct a middle line at the form of an F-curve. In this case, in order to accurately fix the position of the point of greatest profile thickening on the midline, it is necessary to use the option of fixing tangents. The geometry of the steam turbine blade has been improved by improved Abbott's method. This model was tested in Compass Flow simulation software. Our comparative tests show improvements of the average exit speed and the total outlet pressure, 1% and 3% respectively as shown here. We believe that the basic criteria for the aesthetic curves are the criteria of fairness. The other criteria are secondary. There are many of them in technical aesthetics. Your products will be better with the better functional geometry. Thank you for your attention.